Okay, so today I want to talk about physics M2. So no matter what kind of physics you have learned in secondary school syllabus, I don't care if it's HKDSE or IB, I hope that you have learned some physical concepts, and I also have hope that you have known a little bit of calculus. So a little bit of calculus is kind of essential for this course. But even if you don't understand the calculus, I hope that this is actually a pretty good introduction to calculus, because as we know, Newton, a lot of the concepts about calculus, like derivatives and integration, when it was developed by Newton, it really came from physics, right? It came from analyzing projectile motion when Newton came up with differentiation. And the reason he discovered calculus was to better describe physics. So physics and mathematics has always been very deeply connected, but it might be difficult to spot in your secondary school studies, but it will become more and more obvious as you do mathematics in the university. So let's begin. So yeah, so the goal of today is to deduce a lot of the physics formula that you have learned in secondary school using calculus. So we're not going to do that for all the equations, because if you wanted to do that, it would take a very long time. And in fact, in your university, you can, at least in Oxford, choose to understand a lot of the mathematics behind the secondary school concepts. So, for example, if you want to study electromagnetism mathematically, it would be like a year 3 or year 4 course in the mathematics curriculum in university. So the goal of this lecture really is to aim for a fuller understanding of physics, and we're going to talk about rectilinear motion, motion in the 2D plane, like uniform circular motion, projectile motion, and we're also going to talk about waves. And finally, it's going to get a little bit more abstract, and we're going to talk about group theory in physics. So I suppose this might be exceptionally interesting to mathematicians, but again, group theory in physics is actually very, very useful, and it's something that I don't think a lot of people know about. So it's a very exciting thing for me. So let's begin with rectilinear motion. So rectilinear motion, what I mean by that is one-dimensional motion along a straight line. So again, if you imagine there's like a straight line here, and I want to describe the motion of this white object, what I'm saying is that, okay, I only allow this white object to move in this kind of y-axis. So this is usually the framework that we're dealing with in secondary school physics. Sometimes we consider horizontal motion, but for the most part, let's consider vertical motion. And the reason we consider vertical motion is kind of because there's gravity, right? So in AAC physics, we study this kind of vertical motion because there's gravity, and it makes things a lot more interesting than horizontal motion, because in horizontal motion, there's usually, well, there might be acceleration, I suppose, if you're in a car or something, but the most natural example would be vertical motion with the acceleration being gravity. So from calculus, I hope that you know that mathematically we describe the position of this ball as displacement, and we describe it as some kind of function that maps time to this kind of vertical position. And we can take the derivative of displacement to get velocity. So this describes how fast this thing is moving, and then we can take the derivative of the velocity again, and we get the acceleration. So this is how the basic mathematical framework for describing rectilinear motion. And in mathematical terms, Newton's laws tells you certain things. So the first assumption that we're going to make is that mass is constant. This is an assumption that you might not have realized you have made in DSC physics. Is that in fact, if mass is not constant, the physics actually gets very interesting. For example, imagine what conservation of momentum would mean, right? If the mass of an object is changing, for example, if the mass of an object is shrinking with time, then even if the momentum is constant, its velocity would actually keep increasing. So it's actually very interesting. You know, think about what happens to physics if mass is not constant. So anyway, Newton's first law states that momentum is going to be mass times velocity, and we are going to denote that with the function p. And Newton's second law, which is very interesting, says that the force as a function is mass times acceleration. So this is just how we can formulate things mathematically. And in DSE physics, the most crucial assumption is that force is constant. This is extremely important, and that's because force is constant, it means that the second derivative of the displacement is constant. And as such, we can integrate this function to get the first derivative of r, and we can also integrate this again to get r. So even if you don't understand what integration is about, you can think about like if the second derivative of r is a, then what can dr dt be, right? You know that the derivative of constants is going to be 0, and you know that the derivatives of any non-constant function is not going to be 0. And so the only logical conclusion is that dr dt is going to be equals to at plus some constant. So this begs the question, like, what are these constants? What are they talking about? So, well, the first thing that we can do probably is to go to Desmos. So this is something that we recommend people to do whenever you're doing physics or mathematics in general, is to just go to Desmos and play around with what's going on. So in here, I said that RT is 1 over 2 AT squared plus some constant T plus some constant. So maybe we can write it down in here. So if we take acceleration to be minus 9.81, so we want to model this kind of ball falling down, we are going to get, and then we write RT, which so we're just going to write it as like a function of x. So y is equal to 1 over 2 ax squared plus some constant plus some constant. So this is kind of like modeling how some projectile falls down. So this would be, so the x-axis would be the time axis, and the y-axis would be the height. And we can mess with these constants, right? So if I increase c, we're kind of raising the entire graph uniformly upwards, right? If c increases, we're increasing the height. So that kind of corresponds to how high I'm dropping this ball at time equal to 0. So c, in fact, c is exactly the position, the vertical height of this ball at time equals 0. And we can just see this from the graph, right? We don't even need to think about how we prove this mathematically, right? We can just see it from the graph that this constant should correspond to how high this kind of point particle is. Now b is a little bit more mysterious, but we can change it, and we can see it's actually kind of describing the initial velocity of the particle. So if b is 0, then we can see that the ball should start at 0 velocity, right? At time equals 0, it doesn't really move vertically; it just falls down. But if b was positive, then we can see this corresponds to like throwing the ball upwards before letting it drop down. Or if b is negative, it corresponds to I having some initial downward velocity. So the reason I'm doing this is that I want to highlight just how important a graphical understanding of mathematics is, especially in physics. Sometimes you just don't need to do any maths before you get some understanding. And you can obviously check the mathematics later on, but having an intuitive graphical understanding of how maths or physics works is extremely important. So, well, let's try to formulate this mathematically, right? So, again, we can see that when we take the derivative of RT, we get BT, and so we can check that at t equals to 0, the initial, so R0 corresponds to the initial displacement. The displacement when time is 0 is going to be C2, because all these t terms get cancelled out. So C2 means the initial position. Again, with velocity, if we let time equal to 0, we can see that C1 corresponds to the initial velocity. And in fact, if you look at this equation, it might look familiar. This is the familiar Subat equations that you see in DSE physics, right? In HKDSE, they write the initial velocity as u or something like that, and then they write the initial displacement as some other thing, I don't know. Or maybe they expect you to cancel it out, so maybe they expect you to write RT minus R0 is equal to 1 over 2 AT squared plus initial velocity times time. But then again, I mean, isn't it amazing? Like we can understand all we need to know about Subat equations just by looking at this graph. And in fact, there's one more thing that we can do, is that we can also plot the velocity and the acceleration function. So if we plot the acceleration, we plot the velocity, it's going to be like ax plus initial velocity, so it's going to be like ax plus b. This would represent the velocity, and y equals to a, yes, would represent the acceleration. And so for example, how do we understand this graph? So for example, what we're saying is that at time equals to 0, the velocity is exactly at this point. So the velocity at time equals to 0 is minus 0.7. And that makes sense, right? Because minus 0.7 is just the variable b that we've got here. So this would be the initial velocity. And we can see that the velocity decreases with time, right? And this is what we expect. And again, you can mess around with all these variables and you get very interesting results. So I really recommend you to do this. Desmos is just a great tool. So I'm gonna mute Kind, sorry about that, but yeah. So one of the more interesting mathematical things that you see in physics is that energy is conserved. So it's a really it's a really fascinating concept when you think about it, because if you have done HKDS in physics, you know that energy is a scalar quantity, right? But position, displacement, velocity, acceleration, it is a vector quantity. So why does knowing some scalar quantities be able to tell you about how the vector quantities behave? It's kind of crazy, right? You only know one scalar quantity, and it's able to tell you so much about vector quantities, especially in 3D, right? In 3D, the displacement will be like a three-dimensional vector, the velocity will be like a three-dimensional vector. But somehow, if you know the kinetic energy, which is some scalar, and if you know the potential energy, which is also some scalar, it gives you information about the vectors. You're kind of transferring two-dimensional information into three-dimension. So the real framework to understand these kind of things is actually in Lagrangian mechanics, which we will not cover here. But it's something that you really should keep in mind. Like, why can we do this? Why can we translate kinetic? Why can we translate vector information into scalar information? So now we want to show that kinetic energy plus potential energy is constant mathematically in HKDSE physics. And in DSE physics, you might expect that the kinetic energy, well, you know the kinetic energy is going to be 1/2 mass times velocity squared. The potential energy, at least, okay, so this is kind of wrong, but at least for gravity close to the surface of the Earth, we know that the potential energy is going to be mass times gravity, so 9.81 times the height. And because acceleration, we're going to take that to be minus gravity here. So we have like an extra minus sign here. And this is going to be the potential energy. So this is definitely not true in general, right? This is only true when you are close to the surface of the Earth and you're only talking about gravitational force. So let's try to prove this. So this is actually a terrible proof, but this is the most direct proof that you can possibly come up with. And the only thing we're doing is that, okay, well, we want to kind of understand this kind of kinetic energy plus potential energy at some arbitrary time. We just expand the definition, and then we substitute in the formula for R and dr dt that we've got. So because in here we've deduced that dr dt is going to be at plus initial velocity, and this is going to be, and there's also like some formula for rt. We just substitute these formulas into dr dt and R, and then we do a lot of algebra, and we finally get that it turns out that the kinetic energy plus the potential energy at some arbitrary time, and this is important, is going to be equal to the kinetic energy at initial time plus the potential energy at initial time. And so this tells you that kinetic energy plus potential energy remain constant, is kept constant, because no matter what time you throw at the t variable, it's always going to give you the same numerical value as some t0 plus the potential energy at time 0. So the energy is conserved. But again, this is a terrible way of doing things, because you can imagine that energy is conserved in a lot of different settings, right? There's no way that every time you have to do this insane calculation and mathematically prove that the energy is conserved. So there's a much better way of doing this, which we're going to talk about now. So we want to introduce a concept called conservative force. And the idea is that we want to say that, okay, if the force is conservative, then energy is conserved. That's why we're defining this concept of conservative forces. So let's try to understand this definition. So okay, so if there exists a potential function, blah blah blah, such that the force is derivative, then the energy is conserved. So what's the main idea? The main idea that we need to focus on is that the force is dependent on displacement only. It depends on displacement explicitly only. So this is not to say that the force doesn't depend on time. But what I really am saying is that if I'm at this position, then no matter what time I'm at, the force is going to be exactly the same, right? If I'm at this position, the force is always going to be the same, regardless of what time I'm at. And that's really what I say when I say that the force is dependent on position only. So that's what I mean. So the force. So if I know the position, another way of putting it is that if I know the position, then I know the force that it's experiencing. It doesn't depend on time explicitly. I don't need to care about what time we're at right now. So there's actually a lot of very nice examples of conservative forces. And again, the idea is that they're all only dependent on position. So the simplest example would be constant forces, right? If the force is just minus g, well, I suppose you have to assume that the mass of the particle we're talking about is like mass 1 or something like that. Then the force is going to be minus g. And because this is integrable and you can integrate it to be like gr or something like that, this is going to be a conservative force. If we raise the power of r by 1, we get springs or harmonic oscillators. So this is quite curious. So what I'm saying is that the force is going to be negatively linearly dependent on the position. And we can see this with an example. So if I have a spring here, right, you can imagine this point as the position that I want to keep track of. If I increase the distance, then there's a force pulling me this way, right? If I'm pulling here, there's a horizontal force that points towards that direction. So as I pull towards this direction, there's a force going this direction. And this force is dependent, right? If I pull it a little bit, the force is only a little bit. But if I pull it a lot, the force is a lot, right? So this is what I say when the force is negatively linearly dependent on position. Just imagine a spring and pulling a spring. So if you put it this direction, the force goes this direction. That's what I'm really saying is going on in the force. So there's also gravitational force. I don't know if you have seen this before, but the idea is that the gravitational force, at least in like planetary scales, is going to be dependent on 1 over the distance from you to the center of the Earth, for example, squared. So it's actually very interesting, right? Like different powers of R actually corresponds to very different behaviors in the force, but at the same time, the mathematical description of them is actually very similar. But the physical thing that they describe is actually very strikingly different. And the idea of getting the potential is just integrating, right? Even if you don't know about integration, you can just say, okay, well, the derivative of this is going to be this. That's what I'm trying to say. You can always add constants to potential functions. I mean, you have seen this in DSE physics, right? You can change where the displacement is without really changing how the potential functions work or changing how the energy is conserved. So now we're going to do an abstract proof of why, if you have a conservative force, the energy is going to be conserved. And we can see this here. So the idea is that if we want to prove that a function with respect to time, in this case, kinetic energy plus potential energy, is conserved, we want to prove that it is constant. And that is exactly the same as proving that the derivative of it is 0. So that might be a little bit confusing, I suppose, if you have, for example, if you have some function here. So maybe I just remove this. So if you have a function like x squared, this is not constant because the derivative of it, I don't know how to write the derivatives. Well, whatever. Well, I know the derivative is y equals 2x. If the slope is not 0 at all times, then this function is not constant, right? Because the slope kind of measures how much the function is changing at some point. If we want the function to not change, for example, if we want the function to be like a constant function, then the derivative of that constant function is going to be 0, right? So the idea is that instead of showing that the function is constant directly, we want to show that the derivative is 0. And this is actually easier. And the reason is, okay, well, we take the derivative of this. So when we want to take the derivative of squares, we need to use the chain rule. And so we apply the chain rule here. And then we also take the derivative of the potential function using, what is that called? Is it called the chain rule? Yeah, it's still the chain rule, right? We just take the derivative of v with respect to r, and then we take the derivative of r with respect to t. And then in this step, we use the definition of the potential function, which is that the force is equal to the negative of the derivative of the potential function. And so dv dr actually is equal to minus force. And then that is going to be equal to the minus mass times the second derivative of r, and this is by Newton's second law. And so it turns out that these things all cancel out, and so we get 0. And because the only function with the 0 derivative is the constant function, the energy is conserved. So this is a brilliant way of showing that conservation, the energy is conserved, because this kind of strategy works for all sorts of potential functions or force functions, as we see. So again, because in the harmonic oscillator in gravity, the force is a function of r only. From this result, we immediately get that the energy is conserved with some interesting potential function. So this is kind of like how mathematics can be very helpful in physics, right? You can use one abstract argument to describe all sorts of possible cases in physics. So this actually might not still be that satisfying. Like it seems like we just kind of ad hoc this way. Like it doesn't really it doesn't seem obvious. Like it doesn't seem like a person can come up with this. And so a better way of thinking about this is really with Lagrangian mechanics. So you would learn this in university, even if you're just doing physics or if you're doing mathematics. It's a very interesting thing. It's a very interesting way of describing physics, and I recommend you to look it up. So now we want to think about 2D motion. So how do we even describe 2D motion mathematically? So the idea is, again, we use an example, right? So if I want to describe this thing moving around, right, I don't even care about the acceleration or the force or the velocity or anything. I just want to describe the displacement. I just want to describe the position of this thing moving around. Like how can I possibly mathematically do that? And the idea is actually very simple. The idea is that, okay, well, at time 0, where are you? So now, okay, so I say, okay, I'm here. And then at time 0.1, where am I? Okay, maybe I'm here. And then okay, you tell me like where it is. And then time 0.2, again, you tell me where this kind of particle is. And so we do this for all time, right? So the way I describe how this thing moves is that I give you a time, and then you tell me the position. So you can tell me the position in terms of like coordinates, like polar coordinates, Cartesian coordinates, I don't care. As long as you can tell me where this thing is at all times, right? So you can imagine this like a plane movement. So if you can tell me the x and y coordinate of this thing, of this object moving around at all possible times, then you have successfully described how this thing is moving. And that's exactly what we do. So what we say is that a curve is some differentiable function, blah blah blah, that maps time. So the interval is supposed to represent time. Right? I give you time equals 0. You give me something in R2. You give me a 2D coordinate. So that's how we mathematically describe curves. So we're going to again use Desmos because it makes no sense to talk about this abstractly. So the way we do this in Desmos, I don't know if you may know this, is that we say, okay, for example, if you want to kind of represent this in Desmos, we just write T0, and this kind of shows you the curve. So this is actually not very useful. A better way is to write some A0, where A is supposed to represent some variable. We would use this animation mode. It would go from 0 to 1. And what I'm saying is that when A is 0, this point, A0, is at here, right? And as A changes, right, A is supposed to represent time here. The point particle moves. And so what I'm doing here is I want to describe this thing moving with uniform velocity, right? This is what this curve is doing. Is that I'm modeling some point particle moving rightwards with constant velocity, right? So that's really what I'm trying to do with this curve. And there you go. We're now successfully able to describe how something moves in 2D, right? Again, the idea is that we have time. So time is going to be between 0 and 1. So we want to describe the motion of this curve from 0 to 1 seconds. And then we make a function. We have the x and y coordinate depend on time. And we explicitly say what the function is. And we are successfully able to describe motion in the 2D plane. So we can also take derivatives of this. So the idea is that when we take the derivative, again, we want to find the velocity, right? We take the derivative of the displacement to find the velocity. And the idea is actually exactly the same as the one-dimensional case. This time, we just take the derivative of the x-coordinate first. So that would be 1. And then we also take the derivative of the y-coordinate, which is also 1. And this gives us 1, 0. So this is kind of the velocity vector. I mean, you might not have encountered vectors before, but the idea is that there's some thing that points from the origin to this purple point, and that is supposed to represent its velocity at all times. And it makes sense, right? I mean, something moving like this has velocity constant, and it should be some arrow that points towards the right direction, that points towards the x direction, and its magnitude should also not change, right? So that's really the simplest example of curves in RT. So there's more interesting examples, right? So well, yeah, sure. So a projectile under the effect of gravity with initial velocity free fall. So you might not understand how we came up with this kind of with these functions yet, but so let me just show it. Let me see. Yeah, so it's here. So this might be a little bit complicated, right? Okay, my meeting ends in 10 minutes. Maybe we would restart the meeting when it ends. So please rejoin the meeting when the Zoom meeting ends. So this might be a little bit more confusing at first, but again, the idea is very simple. So I might not show this initially. So okay, okay. So you just ignore the k. The k is 1. It doesn't do anything. So so S is supposed to represent displacement, V is supposed to represent velocity, A is supposed to represent acceleration. And we deduce these by differentiating S with respect to D. Right? D is supposed to represent time here. So we differentiate this, we get 4 minus 9.81, D, and then we differentiate it again, we get minus 9.81. So this is kind of supposed to represent gravity, right? The acceleration vector in projectile motion is going to have 0 in the x-coordinate, and it's going to have minus 9.81 in the y-coordinate. And so the acceleration vector, the acceleration, okay, this is not good. Okay, but maybe I'll still use the S plus 1. So the acceleration vector is constant. So in this kind of animation, I've actually repositioned the origin to be at the point. So because this kind of looks better, this kind of looks more interesting. So the acceleration vector is still constant. It's just because this point is moving. So that's why the acceleration vector seems to be changing. But the point is that the acceleration vector is actually constant. And again, the velocity, you can imagine this as some kind of vector that originates from the point. And it kind of looks nice, right? The velocity vector is proportional, is parallel to the kind of path that the projectile is taking. And that also makes sense, right? I mean, if you're going towards this direction, then obviously the velocity should match that direction. Otherwise, it wouldn't make sense. The projectile path shouldn't line up. So again, this is kind of how we understand projectile motion. This is how we describe motion in the 2D plane. So we will understand how we deduce these quantities later. But again, I mean, just looking at this graph, you can already say so much about projectile motion. So finally, we would also talk about like balls uniformly rotating around the origin. So we can actually just do this with another graph. So if I have something like cosine A, sine A, so let me just write this down correctly first. Okay. So maybe in your school mathematics, you have learned how the unit circle corresponds to trigonometric functions, and the idea is that as A changes, so for example, A is here, the cosine function gives you the x-coordinate of this thing. So it just goes around the circle like this. So maybe you can look this up if you haven't seen this before. So this is like the trigonometric unit circle. In fact, I can actually just show you maybe like a diagram somewhere. So trigonometric unit circle. This is not very useful. But okay, this works. So it's really just that, you know, you have some cosine here. This is supposed to be the cosine function. This is going to be the sine function. And so as I change time, it's going to just move around the circle uniformly because I'm changing the time, which is the angle, uniformly, right? The time changes linearly, and so we have this kind of nice uniform circular motion. So we're actually going to talk about this later on as well. But yeah, this is really just how we describe 2D motion, how we describe things moving in 2 dimensions. And you can kind of see that this kind of thing. So okay, well maybe I can write T here. So this kind of shows you the full trajectory from 0 to 2 pi. And so you might think that, okay, well, these are also simple. It can actually be very complicated. So if I throw in a 3 here, it already looks very much more, it already looks a lot more interesting, right? So you can actually see this explicitly. And it kind of moves around in a very chaotic kind of manner. So you can see this point, it just kind of moves around and oscillates back and forth. It's a very interesting movement. And if you increase this number, so you go to 4, then there's kind of like one more loop. And maybe you can try and generalize this pattern yourself. Just play around with Desmos, right? You can learn so much just by playing around with Desmos. So we have 5 minutes left. So so we would restart this meeting, but anyway. So again, the idea is that assuming that the force is constant is extremely important, and this is true in projectile motion as well. So again, the assumption that we make is that so at least for projectile motion, we make the assumption that the acceleration, which is the second derivative of r with respect to time, this is just a notational thing. So this means the second derivative of r with respect to time. This means the first derivative of r with respect to time. The second derivative of r with respect to time is going to have 0 x component, and what that means is that there's no acceleration along the x-axis as it is on Earth, but there's going to be acceleration with respect to the y coordinate. So there's going to be a negative acceleration pointing downwards. And then we integrate these kind of functions. And the way we do it is that we just integrate. So how do we get this, right? We integrate the x coordinate, we get some constant. We integrate the y coordinate, we get some function, and then we just put them back together. So it's the same idea as last time. We just need to do this process for 2 variables instead, and then we just put them back together. So again, these constants, what do they correspond to? They correspond to initial position and velocity. And we can actually see this. So I mean, you can just see it here. When t is 0, the initial velocity is going to be some c1 star, c1. When time is 0, the initial displacement is going to be c2 star and c2. So we can see this in a better way. So maybe we can, well, let's just use the example that we had back here. So maybe let's think about, so changing the initial position is not actually that interesting, right? I mean, you can imagine that if I change the initial position, this entire graph is just going to be translated in some manner. So I don't think, so I mean, you can play around with this, changing the initial position, but you can see that the initial position really is just some constant function, right? You're just adding some constant coordinates to this kind of curve, and so it just corresponds to translations in the plane. What's more interesting is perhaps changing the initial velocity. So let me maybe try and do this right now. So if I have an a variable, if I have a b variable, and now I have to replace a and b here, a, b, a and b. Okay, now we can change the initial velocity and now we can change the initial velocity. So for example, if the initial x velocity increases, then as you can see, this okay, this is not supposed to, I'm not supposed to do that yet. So you can see that okay, what I'm trying to do. So you can see that the projectile now moves in the x direction much quicker, right? So that's because the horizontal velocity is increased, and we can see that the horizontal velocity really just corresponds to how kind of shrinked. I'm really just shrinking the x coordinate, right? And that kind of makes sense. You might be able to think about it, and yeah, just think about it, and it should make sense, right? So and you know this from DSC physics, right? From DSC physics, you know that the horizontal distance traveled is linearly dependent on the horizontal velocity. So what I'm saying is that there's a linear relationship between the initial velocity, the horizontal component of the initial velocity, and how far horizontally this thing travels. We can also change the vertical velocity. So I mean we can go, if the initial vertical velocity is downwards, then obviously it's just going to go down immediately. So it's very similar to what we've done for the one-dimensional case. And in fact, you can actually correspond them. Like why does this look so similar to the one-dimensional case that we did earlier? So why does it all look so similar to this scenario? So you really can think about it later on. I encourage you to think about it. So how can you correspond this kind of description of one-dimensional movement to this description of two-dimensional movement? And the core idea is that the hint is that it is all because the horizontal velocity is kept constant, or that there's no horizontal velocity. So that's really the idea is that again we're able to describe 2D motion, at least uniform, at least projectile motion with uniform acceleration and uniform horizontal velocity with the same exact framework, where we just integrate kind of more complicated things. But again, the operation is still extremely similar. We just integrate two coordinates separately and then we put them back together, or we differentiate two coordinates separately and then we put them back together. So why is energy still conserved, right? It's fascinating, right? Well, why is energy still conserved? So again, the now expressions for kinetic and gravitational motion energy is a little bit different now. So because so let's say that the displacement function is some xt, y, and t, then the velocity, we're going to again take the derivative of this, put it into x coordinate, take the derivative of that, put it here, and then we combine them together to form this kind of coordinate. So the velocity kind of changed a little bit, and because in the kinetic energy, what we're measuring is actually the magnitude of the velocity vector. So this was not a problem in one dimension, because in one dimension we can just square the velocity and we get something positive. But in here we actually need to measure the magnitude to some extent. And so the kinetic energy is now going to be the distance of this vector, which is going to be like the square root of this squared plus this squared. But then in the kinetic energy, we need to take the square of that as well. And so we get this kind of mathematical formulation, which is just 1/2 mass times the square sum of x, derivative of x and derivative of y. And the potential energy is still the same, because this time, at least in the case of like constant, at least in the case of projectile motion, where the acceleration vector is just this thing, the gravitational potential energy is still going to only be dependent on the y coordinate. So it's going to be mass times gravity times the y coordinate. And again, we can show directly that the energy is conserved. And the way we do it again is that we know what the x and y functions are. We substitute them into the definition of kinetic and potential energy. We do this horrendous calculation, and we show that again, similarly, no matter what time you're at, it's still going to be, the energy is still going to be the same. It's going to coincide with the energy at initial time. So again, this is a terrible way of doing things, right? This is just not intuitive. It's not satisfying. The better way of doing this is actually using a more abstract argument that we did. So remember, we did something with derivatives. So remember back here, we did something with derivatives. And this was actually quite abstract. We had the definition of a conservative force. You can do this for two-dimensional motion as well. But again, it involves some heavy calculus I'm not going to talk about here. But do know that you can do it in a better way, in a much better way than just doing this horrible calculation. So now we talk about the most interesting, well, at least to me, the most interesting part of this section is uniform circular motion. So when I first learned this, I was amazed by it. So the idea is that, well, now we want to describe something moving uniformly around the circle. And the idea is that we just want to describe it. We don't care about velocities. We don't care about the force. We just want to understand how things move around the circle, around the origin in the circle. That's all. So the goal, the initial goal, is to actually describe what the displacement function is going to be like. And then we are going to deduce. Yeah, hello. Yep, I can hear you. Okay. Yeah. Okay. Oh, maybe I'm going to mute you. Okay, sorry about that. Yeah. So the idea is that we want to just describe how this thing moves, and then we're going to talk about the force and the acceleration and the velocity later. So to describe how it moves, again, we just think about this, right? We think about how do we describe this, And so there's really only two things going on, right? So with uniform circular motion, especially, there's only two things going on. There's how big the radius is, right? And there's also how fast it is moving. So you can think of it as the angular velocity, right? It is just the radius, and the angular velocity completely determines the behavior. Like if I ask you to describe uniform circular motion, there's only two things you can change. That's the idea. You can either change the radius, or you can change how fast the thing is going. Once you know those two things, you know everything. That's it. All you need to know is these two things. And so we expect that we were able to deduce all physical quantities. We're going to be able to deduce the energy, we're going to be able to deduce the force, we're going to be able to deduce the energy, the force, the velocity, whatever, using these two variables alone. We want to describe everything about uniform circular motion using the radius and the initial angular velocity or something like that alone. And the way we do this is that we actually just parameterize RT as R cosine KT, R sine KT. So you might wonder, where do these things come from, right? The first thing you might be able to understand is the R. So again, let's just use Desmos. Again, you should always use Desmos. This is a recurring theme of this lecture, is to always use Desmos. So we already know the unit ball case, which is just cosine A, sine A. Maybe I have some R here. Again, I have to do this again for the T case because that's just how Desmos works. So let's say R is 1 again. Okay, this also needs to be within the bracket. Annoying. So 0, 1, 0, 1. Okay. So again, I mean, you already this is really annoying. Okay, let me just do this then. Yeah. So you already see this, right? You've already seen this. So when R is 1, this kind of just describes a uniform circular motion, right? It describes this kind of thing moving around the unit circle. So if I change R, so the R can be maybe we say that R is positive. So if we change R, we're just changing the radius, right? We're just changing how large the circle is, and it kind of makes sense, right? We're just multiplying the coordinate by some scalar value, right? We're just magnifying its magnitude. So the only other interesting thing that we can do is actually to change how fast this is going. And I don't know, maybe you kind of already know kind of why we would do this, but the way we do it is to actually just multiply something in a k variable. Okay, I need to do this as well. This was just quite annoying with these kind of brackets. It's actually quite frustrating. So now we have some variable k as well. So even if you don't understand why we're doing this, again, we can just see this visually. Right? We can do everything visually. We don't need to do things mathematically here. So if k is 1, we get what we are used to. So again, to recap, this is the projectile. The green path represents the total movement that the projectile from time equals 0 to time equals to 1. So time is fixed there. So we are always talking about where this thing is moving from 0 seconds to 1 second. So we're not changing the time, at least for now. If I increase k, we can see that it actually moves further, right? From in 0 to 1 second, this thing moved further. And in fact, it moved further by exactly double the amount. So in here, when k was 1, it moved to like maybe somewhere like here. When k is doubled, the distance traveled doubles. Right? When k is, say, halved, the distance traveled is halved. So we already can see that k is supposed to represent velocity. K represents velocity. K is related to velocity. I don't know what velocity it is. I don't know if it's related to angular velocity or who cares. All I know is that it should correspond to velocity, right? Because again, k corresponds to the distance traveled linearly, and the time is not changing, and so that means that k is related to the velocity linearly. There's a linear correspondence between k and the velocity or the distance traveled because we are talking about constant time. So again, this already describes everything we want to do, right? Again, you can change r to whatever you want, you can change k to whatever you want, and this already mathematically describes every possible uniform circular motion that you ever want. to describe. So you might say, okay, well, what if this moves like anti-clockwise or something like that? Well, we can actually just change k to be negative. And again, I mean, it's the same idea, right? Instead of a positive velocity, if you had a negative velocity, then the graph just flips. So we really are able to describe all forms of uniform circular motion. So now we just need to understand, okay, well, what does this k represent? We know r represents radius. What does k do? So the first thing we might do is actually to calculate the velocity and the acceleration. And again, we do this by differentiating, right? We differentiate r cosine kt. We use the chain rule. Even if you don't know the chain rule, you can maybe just take this for granted. We get minus rk sine kt, and then we take the derivative of that again, and we get minus rk squared cosine kt. So we do this for the y coordinate as well. And so we already see something similar, right? So you can kind of see that the magnitude of acceleration is some rk squared. So this might remind you of something if you already know a little bit about this. And indeed, again, we can just calculate the magnitude of these kind of vectors. So this is displacement, this is velocity, this is acceleration. And so not only do we know that the magnitude has this kind of interesting relationship between them, we can also see that they're all parallel. So you can see that this vector is parallel to this vector just by using the slope argument. Just by using the slope argument. The slope of this is going to be like sine over cosine. The slope of this is going to be like cosine over minus sine. And so because you know that the slopes of perpendicular lines are going to be like -1, something like that. And so you can see that these three vectors are actually perpendicular. So let's actually see this. So here we go. So I've done nothing here, but so the radius is actually I'm going to fix the radius here. I renamed k to w, and these two representing time, right? So the green letter here is supposed to represent velocity. So the green vector is supposed to represent velocity. The blue arrow is supposed to represent acceleration. So at time equal to 0, the velocity points this way because we're kind of moving anti-clockwise, and the acceleration vector points towards here. And the variable that we can change is k, so we rename it w. So you can see that if w is smaller, then the velocity is smaller, and the acceleration is smaller. If the w is increased, then it moves around a lot quicker, the velocity is increased, and acceleration is also increased, right? So yeah, that's literally everything. And maybe we can just let this play around. Okay, this is crazy. Let's not change w. Okay, yeah. So again, you just play around this. I can encourage you to play around with this in this place. Okay. So now, what is k? So it turns out the k is angular velocity, and the way we can show this is that, well, what is angular velocity? The angular velocity, when we were thinking about it, is angular velocity is just the angular distance divided by the time taken to travel that distance, right? So if I say that the angular distance is 2 pi, so this is using the radian notation, then I need to divide by the time taken to go around the circle. So and we can see that the time taken to go around the circle is 2 pi over k. And the reason is because for cosine to go from 0 to 0 again, so I mean we can just plot the cosine graph here. Right, cosine dot x. For cosine to go from 1 and it goes down to go back to 1 again, this distance is exactly 2 pi over w. So we can actually see this on here, right? It's exactly 2 pi over w. And no matter what w is, it's going to go back to where it's supposed to go. So it's going to go back to the original position. That means that it traveled around the circle once, exactly, in 2 pi over w time. And so that means that the angular velocity is actually k. So and this makes sense, right? You learned from DSE physics that the magnitude of acceleration is r times the angular velocity squared. So again, you can deduce everything you've ever learned in DSE physics about uniform circular motion just from this alone. So finally, we want to talk about waves. So waves. So fluids in real life are studied by fluid dynamics. I'm saying nothing. But the equations that govern them is actually very complicated. So So there's a thing called the Navier-Stokes equation, and that describes fluid motion in any possible way. So if you have a fluid, you can pretty much study it using Navier-Stokes equations. They describe any possible phenomenon you can possibly think of. But they're very complicated, but that's actually not true. But Navier-Stokes is already very complicated, and so in specific and idealized conditions, we just want to understand waves. Like you see in the beaches, you see waves. They kind of appear everywhere. Let's just understand waves first, right? Like what can we say about waves? We might not be able to say everything we ever want to know about water or how it flows, but maybe we can say something about waves. And this gives us the wave equation. So this equation gives us a specific understanding of waves, and that's all it's able to do. But even that is already too complicated. So what we're going to do is actually just talk about the one-dimensional sinusoidal traveling wave. And so you see this thing. So this is the wave motion you do in DSE physics. So you see this thing, you might already be scared of it, but let's not. So how did we come up with this, right? So let's try to come up with this again in test modes. So even if you have no idea what we're trying to do, the first thing you might try to do is to just plot a function of sine x. So well, in DSE physics, the waves really look like sine waves. Like they don't tell you that, but they do kind of look like that, right? I mean, they're called sinusoidal waves. So of course, they're going to be modeled by sine functions. So this might be the extent to which you might be able to come up with. And then, oh well, how do I model the other waves that we see in DSE physics, right? So the first idea that you might have is that, okay, well, I can actually change how the amplitude of this wave, and that's actually very simple. We just multiply something. We multiply with a. So a is supposed to represent the amplitude here. So if the amplitude is 1, it's gonna have like 1 amplitude. If it's like 2, then it's gonna have like 2 amplitude, something like that, right? So you should be able to come up with this, even if you have no idea about how to formulate waves mathematically. The second thing that you might be able to think of is that, okay, well, I can actually translate this graph, right? So if I translate a sinusoidal wave, it should still be a sinusoidal wave. So and the way we do it is that we just add some so maybe I just write p here. Okay, sure. We just add something to the function, and this is like the graph translations that you might have done in DSE maths. So we're just translating this graph, and we see that, okay, well, we can actually translate this graph wherever we want, right? So if we don't translate anything, then it's going to be here. If we increase p, this corresponds to a translation to the left, and so this wave kind of moves leftwards. Okay. That's great. Now you might think about, okay, well, what if I want to change the wavelength? And again, that corresponds to changing you can think of it as shrinking the x-axis, right? If I want to shrink the wave, I'm just shrinking this function with respect to x-axis. And again, you might remember from DSE maths that we just multiply something in front of the x variable. And again, this is actually exactly what we've done for uniform circular motion. So you should be able to link this up. You might try to do it after this lecture ends. So again, you can see that, okay, if I decrease k, then the wavelength increases. And again, this kind of, okay, well, anyway, and if I increase k, the wavelength decreases. So again, we can already kind of guess what k is supposed to represent, right? You can kind of guess, okay, well, what is k supposed to represent? So what I'm doing here, so this is a picture of the wave at time equals to 0. That's all I'm trying to do. I don't even want to think about how we model this when we involve time. We just want to be able to describe all sorts of waves at time equals to 0. And this already lets us do that, right? No matter what kind of waves you see in DSE physics, we can, at time equals to 0, we can model it. We can model it with this. And yeah, I mean you can just change these variables, and you can get any sort of wave you see in DSE physics, any sort of wave, just by messing around with these three variables. So now the difficult part is actually time, right? We want to be able to describe this thing moving with time. And the way we do it is that, okay, well, because in DSE physics we only care about waves moving in constant velocity, so we actually kind of want something to change like p, right? I mean, if I change p, this kind of looks like something. This kind of looks like the motion that we want to describe in DSC physics. So maybe if I increase P here slightly, right? Like this kind of looks like the uniform wave motion that we want to describe in DSC physics. And it turns out that's exactly right. So it turns out that to describe this kind of movement, all we need to do is to add a minus WT term here. So that's actually all we need to do. So this is some exercise for you back home, because this really is very similar to uniform circular motion. I think you really can do this back home. Just try and understand. So try and prove that the wavelength is lambda is 1 over k. Try and show that the angular frequency is w. It's really not that complicated, because you can really just do it your own. It's really not that bad. What does this psi represent? I mean, you can already guess, right? The psi kind of represents some kind of offset in the initial wave kind of thing. And also, what about stationary waves? Can you think about stationary waves? How you describe stationary waves? Because in here we've described traveling waves, right? So in here we've described traveling waves. What about stationary waves? How would you parameterize that kind of behavior? So finally, I'm going to run a little bit over time. I'm going to talk about groups. So this is group theory. So at first this seems to have nothing to do with what we've been doing so far. But the idea is that in mathematics, there's like a lot of structure. In university mathematics, you learn about structures so much. So for example, you learn about like so in the group course that Marvel has done, we have understood we've kind of been learning the group structure of various sets. But there's actually a lot more structure. There's like, for example, if you want to talk about the area of something, then you would kind of use some sort of how to put this. So, for example, when I'm talking about functions, right? Well, it's actually hard to describe this. So let me think of a way of doing this. So yeah, I mean, okay, I think you should just start with a set. So with anything that you're dealt with, so for example, with a set, what do I mean when I say that I preserve the structure of a set? Well, what I mean by that is that I preserve is that I want to talk about injective and surjective functions. So and that for a set is going to be the set of bijections. So the reason we want to think about injective and surjective functions is because we can kind of they don't really alter the structure of the set, right? It can't do any permanent damage to the set, right? If I just keep applying bijections to a set, it doesn't you can still fix it, right? You can fix it with an inverse, especially, right? That's what we have done in group theory, right? In group theory, but because everything has an inverse, you can kind of fix any damage or any change you do to an object, and because of that, we don't say that the set has been changed in some manner. So when we say that we are preserving the structure of the set, we mean that we do bijections on it, and that gives you a group, right? Bijections give you the group, permutation group. I don't know if you might have seen it in group theory or not, and that's what I mean when I say the structure preserving maps of a set from itself are the bijections. That's what I'm saying. In a group is you're just introducing more structure, right? With a group, with a normal group, if you forget about the group operation, it is just a set, right? So it's when I say that something is a group, I'm actually introducing more structure. I'm introducing an algebraic structure. In this case, I'm introducing a binary operation to some set. And so when we talk about structure preserving maps, not only do we need to preserve the structure of the set, which we can do so by bijections, we also need the bijections to preserve the algebraic structure of the group. In this case, we want to preserve the group operation. And the way we do it is that the way we did it in the group theory is that we had this idea of homomorphisms. That's really what homomorphisms are trying to capture. Homomorphisms want to say that, okay, homomorphisms preserve the algebraic structure. They preserve the group structure of the group. So that's why we get isomorphisms, and isomorphisms are homomorphisms that are also bijections. They not only preserve the algebraic structure, they also preserve the set structure. And that's because the group structure is really built upon the set. If you recall the definition of a group, the first sentence is let X be a set, right? You need a set in order to build a group. And so that's why when we think about things that preserve the structure of a group, we wanted to preserve the structure of a set as well. And that means that it has to be bijection, that it has to be bijections. And so we get bijective homomorphisms, which is isomorphisms. In fact, if you think about Q8 of the first problem sheet, especially the hint, it actually wants you to consider the automorphism group of Z11. So maybe try and read that hint, or maybe ask Marvin in the tutorials what I mean by that. And in fact, in my problem sheet, you will also do some exercises about automorphism groups as well. So as you introduce more and more structure, the maps, the kind of automorphisms you get is you get less automorphisms. So for example, the set of isomorphisms is definitely a subset of the set of bijections, right? Not all bijections are isomorphisms. And that's basically saying that not all maps that preserve the structure of a set preserve the algebraic structure. And that's really just because the algebraic structure is more rich. It's richer than the set structure. When you impose more structure, the maps that preserve that structure is obviously going to decrease as well. And we actually see this in all sorts of things. So, for example, in Rn, there's like 5 different structures you can put on it. You can put the projective space structure, you can put the topological structure, you can put like a differentiable structure. And so I'm sorry if this section is kind of like, especially for physicists, you might not understand what I'm talking about, but that's fine. This is beyond this is really just a optional kind of thing. So if you have done some real analysis or some topology or some whatever, you have all these sort of automorphisms, and the idea is that for example, continuous functions with inverse continuous, they preserve the topology of R. Differentiable functions with inverse differentiable, they preserve the differential structure of R. And so we see that and so in mathematics, the things we study are these kind of functions. Like in group theory, we spend so much time talking about homomorphisms. In analysis, we spend so much time talking about continuous functions or differentiable functions. And that is actually very interesting. If you think about it, we actually spend more time talking about the automorphism group than we do talking about the structure. And in fact, the structure is very boring, right? In all 5 of these structures, the set is exactly the same. It's still Rn, right? No matter we're talking about the differential structure, no matter we're talking about the topological structure, or the vector space structure, it's still Rn, right? So many mathematics live in Rn. So Rn itself is actually not very interesting. Like it's just a set. What is interesting is really the automorphism group of that structure. It is the continuous functions that are interesting. It is the differentiable structure. It is the differentiable functions that is interesting. It is the linear maps, the matrices, that is interesting. And so there's a very famous quote, which is that structure preserving maps. So what I mean by that is the automorphism group. It's actually more interesting than the structure themselves. So whenever you see some structure in mathematics, always think about what is preserving that structure. What are the maps preserving the structure? What can you say about them? It is almost always the structure preserving maps, the automorphism group, that is more interesting than the structure or the definition of the structure itself. Just think about groups, right? Again, the isomorphisms are so much more interesting than the definition of group. The definition of group is actually kind of boring to some extent, right? So yeah, that's kind of what I wanted to say. So how does this have anything to do with physics? The idea is that let's think about the automorphism of some ideal subset of the set of all physical phenomena. So this is a physical phenomena, this is some physical phenomena, and we want to think about how we change the world so that physical phenomena is still possible physical phenomena. So for example, if I translate this entire universe by 1 meter, is the universe going to change? Not really, right? Everything is still going to be the same. I can rotate this entire universe around myself 60 degrees, and this entire universe is still going to be exactly the same, right? Physical phenomena that could happen in this universe can still happen and would still happen in a universe that's 1 meter shifted to the right. But this is actually quite non-trivial. So there's a very famous question which is asking that There's a mirrored image version of this world, the same as the mirror image of the current universe. So imagine that if I have this massive mirror, right, and I reflected the entire universe, would the universe still be the same? Right? Would everything still be the same? So you might say, okay, well, maybe the things you see are going to be reflected along the mirror, so you would be able to spot the difference. But your brain is also reflected. Your eyes are also reflected, right? Your entire body is reflected. So would you really be able to tell the difference? And the answer is actually quite surprising. It's no. And this was done by Wu, which is a very famous Chinese-American physicist, and they actually got the Nobel Prize. So this is really not a trivial question. But in a group setting, I really recommend you reading the story about Wu. It's actually very fascinating and inspiring. But the idea is that, what I'm really asking is that does the reflection group, Z2, belong in the automorphism group of this entire universe, right? It's a very simple question in group theory, right? It's just asking a very simple group, like the reflection group, and whether it belongs into the structure preserving maps of this entire universe. So this is all kind of waffle. Let's talk about an explicit example. So if I have the differential equation minus g equals the second derivative of r, you've already seen this. You know the solutions. The solutions is going to be like minus g over 2 t squared plus constant t plus constant, and I have some solution rt. You know that if I translate the entire solution upwards, or if I translate the time variable backwards, it's still going to be a solution. And what I mean is that if I have some object falling down, if I translate this entire universe by 1 meter in above, so if I add 1 meter to this kind of solution curve, it is still going to be a solution curve. It is still a possible physical phenomena under Newton's second law. So I am allowed to move. So I'm in a one-dimensional case. I'm allowed to move things upwards and downwards, and I can imagine this as moving the entire universe to some extent, upwards and downwards. Obviously, this is wrong because if I move 1 meter upwards, technically the gravitational force is slightly weaker. But whatever. Let's pretend that doesn't matter. What I'm saying is that if I raise this entire room by 1 meter, then the physical laws still hold. Or I can reverse the time. So this is what we call time reversal. So what I'm saying is that if I do this experiment 1 second later, the path is still going to be exactly the same. Everything is going to be translated 1 second into the future, but the projected path is still the same. And in fact, we can actually generate all solutions to this kind of motion from this function alone. So we can imagine. We can imagine if we change the time variable. So now we will have some like minus g t plus b squared, and then we add some constant. Well, this recovers the two constants that we have been doing that we have. So this recovers the two constants that we had in here, right? If I add something to the time variable and then I add something laterwards, I can get exactly all the possible solutions to R and T. This is the same concept as completing the square of a quadratic function, right? And that's actually very interesting. So somehow, if we can understand this kind of function, then all we need to do is to do some physical translation or to do some time translation, and we can get all possible physical phenomena that we can ever want to describe in this very idealistic case of movement. So rigorously, we are actually trying to think about the automorphism group of differentiable functions such that the second derivative is minus g, and we actually get groups. So you're going to do this in the problem sheet, and the idea is that time translation actually forms a group, and position translation also forms a group. We call these Lie groups. So it's a very fancy name. Lie is a person, and he did research on these kind of things. But the idea, what Lie groups really mean is that they're continuous groups, so they're kind of like infinite groups, sort of. And the idea is that these kind of automorphisms, it's a group structure. Again, as we say, automorphisms are always a group. So you can prove this, or maybe you can try and understand why this is the case. So because the automorphism of this set is also a group, we actually have some very interesting group structure here. And these group structures, as you might be able to tell, they can tell us a lot about physics. So is that chat? Lorentz boost, yeah, so true. Lorentz, yes, in fact, Lorentz there's also a Lorentz group. So what I'm trying to point at here, this is the Galilean group, kind of. But there's also the Lorentz group, and in fact, the Lorentz group, the group contraction of the Lorentz group is the Galilean group, and then that's what I'm basically saying is that if the velocity is much slower than the speed of light, then the Lorentz group actually just gives the Galilean group. And again, you can see that this kind of group structure is very important and interesting. For example, the idea is that because using the Galilean group, we can deduce all the solutions from this thing alone. It kind of tells us that if we understand this, then we can use some symmetry to understand the rest of physical phenomena. So that's really why Galilean group or the Lorentz group or like a lot of other similar things like this is very interesting. So if you want to check this out, maybe when you're studying in university, you can read Peter Yates Hayden's book on symmetry methods for differential equations. So that's all I want to say. We've covered advanced mathematics in rectilinear motion, projectile motion, and waves. In the next two lectures, you will see electromagnetism. In fact, they are also about group theory. So they are about a very advanced math theory called gauge theory. And so the idea is that there's actually a group. So U1 is the complex unit circle group. And it is actually hidden. It is a symmetry group of electromagnetism. And Yang-Mills is the mathematical formulation of the standard model. So everything you know about in particle physics, like muons, gluons, stuff like that, they belong to the standard model. And in the standard model, the equations governing them is called Yang-Mills. And there's actually a bigger group, SU2. This is kind of like the special unitary group of order 2. So this is kind of like 2x2 invertible matrix E, something like that. And yeah, and in fact, the Lorentz stuff belongs in electromagnetism as well. So in fact, a lot of the things in electromagnetism, because electromagnetism deals with the speed of light, right? So the right framework to understand electromagnetism really is incorporating something about light speed. And so to understand that, you actually really need the Lorentz group, because the Lorentz group describes the symmetry of 4D space, the Minkowski space. Anyway, but yeah, that's all I wanted to talk about. So yeah, that's the end of the lecture.